Okay, the speaker for today is Mor Rozner. She's a PhD student and Azrieli National Fellow at Technion, Israel Institute of Technology. So besides planet migration, she also works in like meteor-sized objects barrier and the origin of Pluto-Charon system. So today we will hear she talk about the origin of hot and warm Jupiters from inflated eccentric migration. Before more start, I have a reminder. If you have clarification questions during the talk, please raise your hand or type them in the chat. And please keep your long questions to the end of the talk. And you may also want to turn off your video to save the bandpass during the talk. Okay, without further ado, let's welcome Mor.
Okay, so thanks very much for having me here. Please try to ask questions during my talk because it's night here and I might be tired. So try to keep me awake. Okay, and by that I will start my talk. Everyone can see everything and hear me, I think. Okay, so today we'll talk about the origin of hot and warm Jupiters from inflated eccentric migration. This work was done by me, Hila Glantz, my advisor Chagai Peretz, and Evgeny Grishin. Okay. So for many years, people thought that planets outside the solar system, which are called exoplanets, will form and behave similarly to the planets in our own very own solar system. However, not so long ago, still before I was born, on 1995, there was found the first exoplanet ever to be discovered, which is 51 Pegasi b, and it was actually nothing like expected. It was a very strange planet, but later on turned out to be very abundant type of exoplanets. It was a hot Jupiter, and how to form them will be the main theme of my talk today. Since then, more than 4,000 exoplanets were discovered, as you probably know, and they are very different from the planets in our solar system, which we expect the exoplanets will behave similarly. And we have a complete whole zoo out there, including gas giants, Neptune-like, super Earths, terrestrials, and many, many others. Okay. So how to form a gas giant? We will focus on gas giants, and there are two ways to form them. So one option is via gravitational instability, which is a direct collapse of gas phase to massive planet. And the other one is core accretion, in which we have a collision and coagulation of smaller objects. Okay, and we will focus on core accretion. Okay, so how core accretion works. So we start from the core, obviously. And then we have an atmosphere formation. We have an hydrostatic growth, which is this stage, and things go up, and we exceed the critical core mass. And from this stage on, we have a runaway accretion, in which the wannabe planet will accrete more and more and more mass, and then the disk will disappear. And we finish this stage. You should remember this one. This will be the gun at the first act if you want. So in this stage, the planet is very, very big. I mean, at the end, we expect to have something like 1 Jupiter radius, but on this stage, we can have 4 Jupiter radii or even more. And from this stage, the disks disappear, and we have within Kelvin-Helmholtz timescale, we have a contraction, and then we have, for example, the Jupiters that we all know and love. Okay, so what are actually hot and warm Jupiters? I will start from a short introduction and explain what are actually those creatures. So as you might expect, a hot Jupiter is actually a Jupiter. Its radius and mass are in the order of magnitude of the parameters of our own Jupiter, but as you expect, it is hotter. So while the temperature of our Jupiter is around 165 Kelvin, the effective temperature of a hot Jupiter is around 1000 Kelvin and might even be higher. The temperature of a warm Jupiter is around 500 to 1000 Kelvin. Moreover, hot and warm Jupiters are very close to their host star, as you can guess also from the temperatures, and the periods of hot Jupiters are 10 days or less, and of warm Jupiters are between 10 and 200 days. You can see the population of hot Jupiters on the left corner, if you can see my cursor, inside there. Okay. So it turns out that hot and warm Jupiters, those strange exoplanets, are abundant. The first exoplanet ever, as I told you, to be discovered was a hot Jupiter. And since then, around 10% of the discovered exoplanets are hot Jupiters. So I should say that it is partially because of the bias towards them. but warm Jupiters and hot Jupiters are abundant regardless, and warm Jupiters are less observed due to biases, but are expected to form in at least similar rates as hot Jupiters, as can be seen in this figure, which is taken from observational data. Okay, and it is important to note that most of the hot Jupiters are observed to be almost circular, which might be a result of tidal evolution. And so this is the second gun on the second act or something. Okay, and some of the warm Jupiters appear to be more eccentric. Okay. So actually, it seems that I told you already what are hot and warm Jupiters. So what are the main problems? It turns out that their formation is puzzling. Why? Because they are very close to the star. And how did they actually get so close to the hot star? Maybe they were born far away and migrated later. And if they migrated, how they do it? Okay. So as always, we have several explanations. So I will show you the three main channels, formation channels. So
we have a question in the chat. Bradley asks, why are worms expected to have comparable rates that must depend on some assumption?
Yes, okay, so I'm not so into observations, but as I think, well, there is a measured rate of hot and warm Jupiters. I'm not actually sure how they did interpolate the observational data, but I am pretty sure there was a very detailed review by, I don't remember what was the first author, but Rebecca Dawson was one of the authors, and it was out on 2021. I mean, just several months before. So I should check there and go back to you later on. Maybe when it will be okay. So that's it, I guess. Okay, so I have no good answer for that. Yes. Okay. Okay. Okay, so we know now what are hot and warm Jupiters, and it is time to discuss their origin. So one option is to form them in situ near the star. While this might be a reasonable explanation for a significant part of the warm Jupiters, between 30 and 90% of the expected rate, you can check Wang et al. 2016 if you want. The expected rates of hot Jupiters from this channel are too low. And there are also models which suggest that they formed far away from the star and migrated later. Okay, and if we are talking about migration, there are two types of migration. We have disk migration and high extrinsic migration. So disk migration describes dissipation due to interaction with the gaseous disk. High extrinsic migration describes dissipation of energy due to tidal forces that leads to migration and circularization. Okay, so those are the three approaches, channels if you want. And we will focus on high extrinsic migration, tidal migration, which is this one. Okay. So there are two phases in the tidal migration actually. So there is the first phase in which we have angular momentum dissipation, in which we excite the planets or Jupiters to high eccentricity in order to initiate the second stage, which is the energy dissipation tides. Okay, so we need high eccentricity. How we can maintain high eccentricity in Jupiters? So one option is the quasi mechanism, okay, which is secular or other kind of secular interactions, which means perturbation from another faraway object. And another option in which we will focus is planet cloud scattering, and it's time for a movie. We will cooperate. Yes, okay. So what you can see here are two stars or planets. Can you imagine what you want? They get closer, and then one is scattered far, far away, and we are left with one eccentric planet, still orbiting the star. Okay, so that's it. And this is visually how planet scattering works. Okay. So why are eccentric binaries so interesting? They are very abundant, and there is a large variety of scales. For example, they play a role in eccentric migration, and this is why I showed you and discussed later. We have close interactions and collisions and formation of close or contact binaries, and now we'll take a side step actually and talk about, okay, so we have an eccentric binary, for example, in Arrokoff, which was observed not so far ago. And another option is maybe the most famous Kuiper belt binary, Pluto-Charon, and it is an eccentric binary as well. We had a work back then suggested it started from a wide binary, and due to secular evolution, it got closer. And there are ton of many other options like of dissipation, like gravitational waves, and many, many more. Okay, so back to hot Jupiters. So it seems that actually I've already told you what is the problem, how to form hot or warm Jupiters, and what is the solution to form them via tidal migration, for example. So what will be the rest of my talk about? So the problem, or at least one of the problems, is that sometimes the migration takes way too long. So here you can see two examples of migration, and you can see that the timescales here are very, very large. I mean, hundreds of million years. And we want to form the hot and warm Jupiters in much shorter timescales in order to explain the observational data. Okay, so how do we do it? As I told you, it is still hard to retract the rates. So sometimes the migration takes too long, and not all the migrating planets end as hot or warm Jupiters. Sometimes they are still migrating after a Hubble time. So what we need to do, we need to extend the parameter space, but how will we do it? So as I told you, some of the Jupiters are born inflated, and then we have contraction or cooling in timescales 1 to the 7 to 1 to the 9 years. Okay, and we suggest to discuss initially inflated Jupiters. So gas giants, including hot and warm Jupiters, are born by a co-accretion in which they reach larger radii than Jupiter radius. And at the end of the co-accretion, the migration starts, and it is more efficient since the tidal forces scale as fifth power. For example, for weak tides, you can apply the very same mechanism for other options of tides, and there are many other options, I mean, like chaotic tides or dynamical ones. Okay, so we have a fifth power of the radius, which will be very important when we calculate the timescales of the migration. And this thermal contraction phase is usually overlooked in the discussion of the origin of hot Jupiters, but was mentioned by works by Wu and by Petrovich. And it is shortened significantly the migration timescale, and hence the formation rates might increase. So it seems very, very good and promising. So here you can see a model of a shrinking hot Jupiters. You can see that it starts from 2 Jupiter radii. And by the end of the contraction, we finish the evolution again with the 1 Jupiter radius candidate. Okay, and the contraction timescale is very long. You can look at it something like giga-year even, and such that the hot Jupiter's candidate will stay inflated for a significant part of the dynamical evolution, which is great because we want to keep them inflated during the evolution in order to maintain the great dependence on the radius. Okay, so it's time for illustration. Okay, so I must say nothing for scale, of course, and this is the evolution as suggested by our model. So we have a hot or warm Jupiter, this one. And we start big and far, far away from the star. And during the evolution, it migrates and becomes circular fast due to the large radius and the strong dependence on the radius that we expanded, and contracts slowly within Kelvin-Helmholtz timescales. So we have a fast migration plus a very, very slow contraction, which is great. And warm Jupiters are likely to end their revolution still eccentric after a Hubble time via this channel. Because basically what we suggest here, as warm Jupiters are just, if you want, warm Jupiters that still didn't finish their revolution, or transient hot Jupiters. Okay, so how will we model it? Okay, so we couple the dynamical evolution with the thermal one. The equations of the separation and electricity change are given directly from the tide model, such as weak tides, dynamical tides, chaotic tides. You can plug in with your favorite tide model, okay? And then we insert them the changing radius of the Jupiter. The thermal evolution of Jupiter, which dictates the radius change, is dictated by the incoming and outgoing energies or luminosities equivalently, as can be seen, here, okay? And in order to model it, we have two approaches. So we have the semi-analytic approach, in which we have a tidal migration step. We move to thermal evolution step, which means we have a delta E, the energy, and then we have a calculation of the delta R, tidal migration step, etc. So all in all, what we have is just coupled equation. We just coupled those equations. We have an equation for the dE and dA, and we have an equation to dR. And all in all, we solve them together, and we have a combined evolution, thermal-dynamical evolution. And the other option is integrated with MESA or numeric approach. Using the AMUSE framework, we couple our orbital evolution code with the stellar evolution code MESA and simulate both tidal and thermal evolution. So what we need to take from this slide is that we have two approaches. One is analytical or semi-analytical, and the other one is numeric. Both of them couple self-consistently between the dynamical evolution governed by the tide equations, let's say those one, and the thermal evolution, which is expressed by the change of the radius. Okay, so let's dive a bit into equations. For example, those are the weak tides, and what you should take from here is that there is a strong dependence of the radius on the radius, as I showed you earlier. So we have a fifth power of the radius inside the dynamical evolution equations, which means that the dynamics will change significantly when we consider a contracting planet, because we start of a factor of 2 here. So let's say 2 to the power of 5, we have a factor of 32, which is very significant. Okay. Not Corona, I hope. Okay. So the thermal evolution includes cooling and heating. So we have an incoming heating, which could arise from several sources, such as irradiation, tidal heating, or ohmic heating, for example. There are many others, because one of the problems or puzzles in hot Jupiters that there are found a lot of hot Jupiters with radii exceeds 1 Jupiter radius, even reach something like 2 Jupiter radius or even more. And for now, we don't have a full explanation. So there are a lot of explanations for external energy sources, and those are some of them. And the cooling would be just black body cooling plus insulation corrections. Okay, so together we have a balance between the incoming and outgoing energies, and this will dictate how would the radius evolution will look like. Okay. For the semi-analytical approach, so we have the energy change, and we have basically, just as I told you earlier, you have the luminosity from heating, and now maybe the most important thing from this slide is that the luminosity might depend both on the same major axis and the optical depth, which means if you put the energy at the central parts of the planet, obviously you will have a larger effect. And if you put it outside, you will have much less effect. So if you want to do something the most efficiently, you should put all the energy at the center of the planet. Okay, and we have cooling. Okay, sorry. And from the equation of state, we have the temperature change, which dictates the rate of change. Okay. So briefly on the numerical approach, so we have thermal evolution, which means radius and central temperature. We measure how the planets evolve. This is the thermal evolution time step. And then we move to orbital evolution, which are A and E. And this is exactly the same as the semi-analytic approach. And this is what we call the dynamical evolution step, and go on and on. Okay, so some results. Here we can see results of the coupled thermal-dynamical evolution of a hot Jupiter. The solid lines corresponds to semi-analytical solutions, and the dashed lines to numerical solution, and the dotted dashed, okay, so I told you everything, right? The solid lines to analytic and the dashed to numeric. Okay, and everything with irradiation. Okay, so the numerical simulation ended when the migration practically ended, on other stopping condition. Okay, and generally there is a good agreement between the numerical and analytical results. And you can see that the migration timescales of the initially inflated Jupiters are much shorter than the one with the constant Jupiter radius. So we inject heat also there, but it won't get bigger because it's very hard to have Reinflation, harder than just contract to smaller radius. So you should compare between the blue line, for example, and the orange one. So the blue line corresponds to 1 Jupiter radius, the radius that usually people use, and the orange one to 1.5. And you can see that there is a huge, actually almost order of magnitude difference between them. Okay.
I am sorry to interrupt, but there was a question in the chat from Andrew. Are you including heavy element masses, e.g. cores of Jupiters? Okay,
so at the semi-analytic model, we just assume that we have a planet that behaves according to the ideal gas equation. And we don't get into details of the element masses inside the planet. I mean, we just have energy and we put it directly into the evolution. I don't know if it answers.
Yeah, no, I was just curious because there's work, I guess, in particular by Thorngren and Fortney showing that the heavy element masses of the warm Jupiters are really quite astonishingly high. I mean, up to significant fractions of a Jupiter mass of heavy elements, which obviously affects the radii in significant ways. Another quick follow-up, it looks like your radii are monotonically decreasing. Is there a reason why with high eccentricity, the tidal heating, is it allowed to cause an actual inflation of the planets? Or
okay, so that's a great question because I have a slide explaining exactly about this. So thank you about it.
Okay, sorry for jumping ahead.
No, it's great actually, yes. Okay, so I will answer to you in 2 slides from now. So thanks for the questions. Okay. Okay, so what we should take from this slide, I told you inflated migration is much more efficient. Okay, so that was it, I think. And what the irradiation does, okay, so obviously it does a very important thing, which is to raise the temperature to the effective temperature that we expect to have to hot Jupiter or warm one. Otherwise, we just have a flat or almost flat or just cooling. And not that high temperatures, one way or another. Okay, so let's move on. And this is an example of a warm Jupiter, eccentric one. We finish the evolution at this stage, and you can think it actually about a transient hot Jupiter and not a warm Jupiter in the classic stuff you might think, because we still have an electricity, so in a sense we can still go on with the evolution on, but here we've got yet until a Hubble time, so that's why we stopped simulation and call it a warm Jupiter. So also here, initial inflated radii lead to enhanced migration, and finally less eccentric warm Jupiters. Okay, and the good news are that large radii also increase the total formation rate of warm Jupiters, but this is a spoiler. We shouldn't say it right now. Okay, so I guess this will answer the question that was asked before. So what tidal heating will do? So as you can see here, okay, I should tell you what the lines are. Okay, so we have the red line is without nothing, and the orange line is with tidal heating, which will correspond to what was asked before, the blue line with irradiation, and the green with irradiation plus tidal heating. So more specifically, what tidal heating will do. So when you are far enough from the planet, tidal heating won't do anything. When you are close enough to the planet and you already circularize, tidal heating won't do anything. So it will be the most significant somewhere in the middle. So this is why we have this bump here. And we have slight change, but it won't change much, at least in those cases. And we did also population synthesis. I will discuss it also later, I think. Okay, but irradiation can still keep the planet a bit more inflated for longer times. Okay, so that's it, I guess. Okay. So until now, I talked just about separate individual cases of hot and warm Jupiters, but after all, what interests us is the total form population of hot and warm Jupiters. So to study this, we carried the Monte Carlo simulation based on the semi-analytical model, since it is much simpler and way less computational time consuming than the MESA model, which takes typically 2 days of or so for one simulation, and studied the whole population of formed hot and warm Jupiters and its properties. So what we need to put in. So the initial parameters are the semi-major axis, which we take to be log uniform distribution, the eccentricity, which we take to be Rayleigh distribution, the mass, which we take the power law distribution with power minus 1.1, and maybe the new ingredient in our models, which extends the parameter space, is the radius, which we take to be a uniform distribution, okay? And this is actually the very new thing in our model. And what are the final parameters that interest us? So we have final semi-major axis, or equivalently final period. We have final eccentricity and final radius. Okay, so how will we calculate the rates? So finally, we would like to estimate the rate of form hot and warm Jupiters, and we'll sign it by this curly R. And in order to form a hot Jupiter via our model, we should have a Jupiter around the star, and actually we should have two Jupiters, to be honest. Planet scattering, we need the massive enough planets to get scattered in order to maintain a Jupiter in our system. And we should now check how many systems could invoke planet scattering after all. And finally, we should check what is the fraction of systems from which given distributions of semi-major axis and eccentricity, they are likely to finish their long and winding road of migration within a Hubble time and won't get tidally disrupted. So all in all, the observed fraction of hot Jupiters today is 0.3 to 1.5%, and we expect something like twice the rate of hot Jupiters for warm Jupiters. I still need to check what exactly are the observational constraints about this. And reducing the warm Jupiters that could form in situ, we can retrieve the total observational rate for warm Jupiters. So those are great news because our model works on this stage. But for hot Jupiters, we still need a further channel to complete the picture. And now we should ask ourselves why. Okay. And so maybe I will start on this one and then move to the other slide. So there is no rose without a form. And we increase the rate of migration. The migration is much faster and much more efficient. And in our case of inflated Jupiters, we will get some, but we lose some also. And although, and maybe even because the evolution becomes so fast due to the inflation, we have enhanced enhanced disruption rates. And all in all, it leads to decrement in hot Jupiter's rates relative to the non-inflated planets, but the warm Jupiter's fraction increases. So what you can see here is the tidal disruption rate. So you can see there is a very significant tidal disruption rate also for the one Jupiter radius, but for the inflated one, we have much more. And cold Jupiters, we have less cold Jupiters in the inflated case, and the rate of warm Jupiters increases in the inflated model, and but we have more hot Jupiters in the non-inflated case. So you should think for yourself about the flow in the parameter space if you would like to think about it. So you start as a cold Jupiter, and then if you're lucky, you move to be a warm Jupiter. If you can move more, you become a hot Jupiter, but if you move too close to the star, just like Daedalus and Icarus, you will burn away and tidal disrupt. So that's it. And now we move to this one. So this is the probability density of the final parameters as derived by the Monte Carlo simulation. So we draw something like, I think, million simulations here. And you can see the probability density. So you can see that most of the weight sits on the hot Jupiters. This is the yellow part here. But we have a lot of warm Jupiters here on the blue part. And this curve is derived by the angular momentum conservation I promised you at the beginning, because at this part we just dissipate the energy but keep the angular momentum roughly constant in the stage of tidal migration. And the white vacancies here, so we have this part means that we have two large periods. So this will be the cold Jupiters, if you want, the ones who were not lucky enough to become warm, at least warm Jupiters, and that still have larger periods than 200 times. And here you have all the planets that were unlucky and tidally disrupted. Okay, so let's move on. So an interesting feature also was pointed out by Petrovich, I think, is that inflated Jupiters lead to a shift in the period distribution. So this is an observational signature if you want. So if you have one Jupiter radius planets, their distribution will be like this. But if you have an inflated eccentric migration, you will have a shifted distribution towards the right side. You will have more warm Jupiters. We fill the valley here. And we lose hot Jupiters because they will be tidally disrupted. Okay, so what's next? Both our analytical and numerical models are general. More external energy sources, such as ohmic heating, for example, we can include in our models. Okay, high eccentricity migration initiated by vertical triple interaction, another direction, or estimate the age of hot and warm Jupiters from their current properties. Okay, there are many, many others. You are welcome to contact me and suggest even more. Okay, takeaways. So what you should take about this lecture today. So Jupiters are inflated at the end of core accretion. Inflated Jupiters migrate faster. Inflated Jupiters are prone to further disruption. External energy sources could help keeping hot Jupiters inflated. Migration timescales we derive are short and can reach even less than 10 million years, and we are able to retrieve the observational fractions of warm Jupiters. And that's it. That's how we bring them hot and safe to the current position. Thank you. Okay, so on this stage, maybe I will take questions, move to my backup slide, or talk about other projects. So what should I do?
Let's stop here for a second and see whether people have questions. So please raise your hand if you have questions. So I have one first. So I guess like you start the evolution at 1 AU, I guess the Jupiter will not be tidally locked at 1 AU. So I'm wondering, how do you treat the spin of the planet?
So in this very simplified model, we have a pseudo-synchronized hot Jupiter. Cold Jupiter when we start the simulation, but we don't treat spin evolution. Everything is pseudo-synchronized, but you are completely right, of course. We can, in general, add this equation also. And it will be very easy. We do have all the other equations and just plug it in with the radius change.
Okay, and we have a question from Bradley.
Hey, so looking at your period eccentricity plot, so you're basically predicting that warm Jupiters are substantially eccentric. That's presumably testable. Maybe it has already been tested. Have we?
Sorry.
No, so I'm just asking. It seems to me that's because the classification of warm Jupiters extends out several tens of days, right? So you're predicting planets with eccentricities of like 0.6 and things like that, are you not?
Okay, so obviously they are observed circularized warm Jupiters already. So our model can account only to the eccentric one, but it doesn't mean they are the only one, and there are obviously other evolution channels such as in situ. And there is a decent fraction of warm Jupiters that they are observed in binaries. So this is a smoking gun, if you want, for in situ formation. So I guess in situ formation can complete the picture, and the circularized planet will come from this channel and not from our channel, if it answers.
Fair enough, but right at the beginning, you made the point that the occurrence rate should be similar. So you're tying. If you bring down the fraction of warm Jupiters from your simulation, does it imply that there's a similar reduction in the fraction of the hot Jupiters that are contributed from this channel?
I don't think they are tied in this part, because hot Jupiters are more prone to tidal disruption, and the phase space of warm Jupiter will look different because they don't flow. They flow just to the hot Jupiter side. They don't flow to the tidal disruption side, so you can benefit more from the inflated migration to warm Jupiters rather than hot Jupiters.
Okay.
Do we have any other questions? Okay. I see another question from Bradley. Yeah.
I didn't want to be a hog, but if there's somebody else, so you sort of mentioned in your to-do list something that I'd wondered about, which was you're talking about scattering as your source of your hot Jupiters coming in, which happens quickly, and therefore you could imagine large radii for the incoming planets. If you start now thinking about other channels like secular perturbations and triples, those take much longer timescales to kick in. So you might not expect as large a radii for those planets. They should have cooled more by the time they come in, right?
Yes, okay, so exactly, this is a great point. If the Kozai time would be larger than the cooling time, so obviously you won't see anything, but something interesting might happen in the secular regime because the tides might give rise to quenching of the Kozai. And then the Kozai will stop, the planet will contract a bit, and then the quenching will be off, and then you will keep on with the migration. So interesting stuff might happen on this direction. But they are, of course, systems with Kozai time much larger than the cooling time, and then nothing interesting will happen. Yes.
Andrew?
Hi. Thanks Ian, for the talk. I was wondering if I could just follow up a little more on the issue of slowing contraction versus reinflation. It seemed to be when in the results you showed that you just including the physics that you included, there just was no reinflation. And is that just because the energy being put in is not large enough, or is there some other issue?
Yes, it is exactly. Well, we did a lot of mock tests behind the scenes, and if you put enough energy, it will it will puff up and it might even explode if you give it enough energy. And we tried, well, in the paper we are about to submit, hopefully in the next week, if I will be lucky. So we tried to model efficient heat transfer. So we put something like 1% inside at the center of the planet, and then we can see a small reinflation maybe. And if we have larger percents, you can definitely see reinflation, yes. So if you, yes, the short answer is definitely, if you put enough energy, you will see reinflation. The problem is just energy.
Yeah. So, I mean, one of the, I don't know, at least to me, most surprising and interesting recent sort of observational results, and maybe not that recent anymore, is the indication that, you know, when the stars evolve, become giants, or even as they heat up along the main sequence, that higher level of flux seems to be correlated with what would seem to be a reinflation of the planet. And that's, you know, I think, as you probably know, surprising for various reasons, that reinflation obviously works very differently from just keeping something from cooling. So I'm wondering if your results, where you're not just necessarily heating the planet at the same orbital, orbital distance at all times, if you thought about how that might relate to these reinflation observations.
Okay, so given strong enough source of energy, we expect to have reinflation in that sense, and we can go back to our equation and couple the energy source, and it will be fine, I think, if it answers.
Yeah. I guess the puzzle to me, and if anyone just wants to have a discussion of this, is that at least to the extent that people have, Daniel Thorngren and Fortney and collaborators have determined, everything just correlates very nicely with stellar flux, and not much of a need for an instantaneous stellar flux without much need for secondary parameters. And so that's that's the part that has me sort of confused.
Probably that should be, sorry.
No, I mean, but Mor is talking mostly about putting energy in the center of the planet, right? And if you go back to the old speculations about transferring irradiation to the center of the planet, then everything's fine. The real question is, if it's all deposited at the surface, it's hard to reinflate stuff, right? So that's the question of where is the energy put in the planet?
Sure. Also, how much energy you need, but yeah.
Yes, given much energy on the right place, it will be fine. So if there is a heat transfer that magically or physically moves the energy from the surface towards the center, as done by many other works, and I think, yes, also by Andrew. So yes, there are a lot of mechanisms suggested how to transfer the energy towards the center, and it will solve the problem.
Okay, I think that's, if we don't have any other questions, I think that's good for today. So let's just unmute ourselves and applause for Mor's nicely talk.
Thank you.
Okay, thank you. So it's nice to see everyone, and see everyone next week, next Monday.